Simple plane regions. This is my second lecture on the application of the definite integral to find the area of plane regions that are bounded by curves. So last time I introduced to you how can we apply the definite integral to get the area of a plane region bounded by a curve. Given a function f of x on the interval ab, where f of x is greater than or equal to 0 for all x in that interval, the area of the region, which is bounded above by the curve, bounded below by the horizontal axis from a to b, is given to you by the definite integral. Okay, a is equal to the integral of f of x dx evaluated from a to b. So something like this happens in definite integral. We are given a plane region here represented by A. And so what we do is we produce a partition. When I say partition, it's like partition to divide. Okay, so we will partition the interval into many rectangular strips. As n approaches infinity, you can imagine those rectangular strips to appear to you like line segments, and that rectangle is going to have an area, and that is represented by this. So this one is just the height of your rectangle f of x times delta x sub I, which is the width of your rectangle. So it's going to be something like this. The width, this is delta x, and the height there will be given by f of some x. Okay, so that's why I gave it x with a hat. Some x inside that interval, okay? And so when you do the multiplication, when you get the product, that is just the area of one rectangular strip. So when we get the sum, the limit of that sum, okay, so this is the sum of all the areas of your rectangle inside your partition. So the limit of that as n approaches infinity will approach the area of that plane region. And if that limit exists, that is what we call the integral of f of x dx from a to b. So you can look at the integral sign as some kind of a summation symbol. So how do we do the definite integration? Well, first we get the antiderivative, okay? And then we shall evaluate the antiderivative at the limits of integration. What if our region is bounded by two curves? In this case, it's bounded below by y is equal to g of x and bounded above by y is equal to f of x. The integral that will give you the area of this plane region represented by a is given by this. The integral of f of x minus g of x dx from a to b. So be careful, okay? So you must pay attention to the order of the functions that you are integrating, okay? So you call this the function above the plane region. And this one, okay, is the function that is below the plane region. So this is what happens in this integration. First, what we do is we get the area of the region represented by this, and this is given to you by the integral of f of x dx from a to b. Then, we get the area of the plane region which is bounded above by your function g of x. Okay? That blue shaded region. And that is equal to this. So in order to get the area of this plane region, we do a simple subtraction. The integral of this function, f of x dx from a to b, minus this area, which is given to you by this, and that will give you the area of this plane region. Find the area of the plane region bounded by these two curves. Y is equal to x squared and y is equal to 2x. Well, first we must sketch the curves. Okay? so that you would know what is the function above the plane region and what is the function below the plane region. Okay, and also, of course, you must know the interval of integration. Okay, so in this problem, we are not told what is the interval of integration. So you're familiar with y is equal to x squared, that is just a parabola, and y is equal to 2x is kind of a steep line. This is how your functions will appear in relation to each other, and that region, okay, the shaded region is the region whose area we are working on. Okay, so g of x is the curve that is below the plane region. It is the function that bound your function below the plane region, whereas f of x, which is equal to 2 times x, is the function above the plane region. So the shaded region is the region we are working on. What is the area of that plane region? Now, it's easy to set up the integration, okay? So it's just the integral of f of x minus g of x dx, okay? But the question is, what is the interval of integration? What is the lower bound of your interval of integration, and what is the lower limit? Lower limit of your interval of integration, or what is the upper limit? Well, by inspection, you can tell, okay? The interval of integration is going to be from 0, this is 0, to 2. This is from 0 to 2. But sometimes it's not obvious. Sometimes it's not obvious what the interval of integration is. Sometimes you have to work it out algebraically. The interval of integration are the x coordinates of the points of intersection. Look at this. That's a point of intersection. That's another point of intersection. Okay. 2 is the x coordinate of that point. And this one is 0. The x coordinate is 0. So you can find the interval of integration, at least in this case, from the points of intersection. How do you look for the value of x? So let's say, for example, we cannot see the graph. Okay, we are only given the functions, the equations that define the curve. How do you get those intersections? Well, you know what to do. At the points of intersection, f of x is equal to g of x. Okay, 2 times x is equal to x squared. And when is that true? When is that true? That is true when x is 0 or x is equal to 2. And so what you do is you set up the interval of integration, okay? So the area is going to be the integral of f of x minus g of x dx from 0 to 2. So this is straightforward application of your power rule. So it's equal to this. X squared minus 1/3 times x cubed evaluated from 0 to 2. And you know what to do with that, excuse me? So what's going to happen is this is equal to 2 squared minus 8 over 3 minus, you will substitute 0 to your antiderivative, and that is just equal to 0. So this is just equal to 4 minus 8 over 3, and that is equal to 4 over 3 square units. Some professors are strict about this, others are not. Sometimes they just ignore this. They can just ignore it. But because we are working on area, and the unit of measurement for area, it's square meters, square centimeters, okay, square feet. And that is why some books and some teachers prefer to affix this symbol, square units. So the area of that plane region is 4/3 square units. Find the area of the region bounded by y is equal to sine of x and y is equal to cosine of x in the interval 0 to pi over 4. So I hope that you are familiar with the curves of your sine and cosine functions. So which do you think is your sine function and which is your cosine function? So basically the graphs of your sine and cosine function, okay, you call them sine waves. You call both the graphs of sine and cosine as sine waves because they basically look the same except that they are not in phase. So what do you think is your sine function and what is your cosine function, okay, between these two curves? Well, what is cosine of 0? Cosine of 0 is 1. Cosine of 0 is 1. And what is sine of 0? Sine of 0 is 0. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So the red curve, the red curve is your curve for your sine function. And this gray curve is going to be your cosine function, okay? Well, here we are told the interval of integration. Okay, so it's from 0. So somewhere here, which is the midpoint of 0 to pi over 2 is pi over 4. So that shaded region is the region whose area we must produce using definite integral. Let us set up the integral. It's going to be the integral of cosine of x, the function above the plane region, minus sine of x, the function below the plane region, dx, evaluated from 0 to pi over 4. So the antiderivative of cosine is sine, and the antiderivative of sine of x is negative cosine, okay? Negative cosine of x, that's why it became positive, okay? So minus negative sine of x, no, minus negative cosine of x will give you plus cosine of x, evaluated from 0 to pi over 4, okay? Now, sine of pi over 4 is square root of 2 over 2, plus cosine of pi over 4 is also square root of 2 over 2. Now, minus sine of 0 is 0, minus cosine of 0 is 1, and this one is equal to square root of 2 minus 1 square units.